Welcome everyone to our video on Bronsted-Lowry acids and bases. In this video, we are going to learn about the Bronsted-Lowry theory of acids and bases and how to identify conjugate acid-base pairs. Then we're going to learn about the KW equation and how to do some simple calculations which are going to be convenient for acid-base calculations. You have already learned about the Arrhenius theory of acids and bases. But this theory has some limitations. And whenever a theory in science has some limitations, that's a way of knowing that perhaps there might be a better theory that can be used to explain this phenomena. The Bronsted-Lowry theory of acids and bases is going to address some of the following problems with the Arrhenius theory. The first problem is that Arrhenius' theory depends on the presence of hydrogen and hydroxide ions. This is a problem because there are many chemicals which, when dissolved in water, produce acidic or basic solutions, but do not seem to have those chemicals present in their formula. For example, ammonia, NH3, when dissolved in water, produces a base, but NH3 does not have that hydroxide ion present. A second limitation of Arrhenius theory is that the water molecules which are in these solutions has no role to play. And we will see that, in fact, water does play an active role in the ionization of acids and bases. According to the Arrhenius theory, all salts, ionic compounds such as sodium chloride, should produce solutions which are neutral because they do not have hydrogen or hydroxide compounds. But this is not the case. Many salts, which do not have hydrogen or hydroxide in their formula, will produce solutions which are slightly acidic or basic. Related to an earlier point, the need for this hydroxide ion specifically led Arrhenius to propose that when ammonia dissolves in water, there's a base produced called ammonium hydroxide, NH4OH. This compound has actually not been shown to exist, even though we still refer to a solution in which ammonia is being dissolved in water as ammonium hydroxide. The acid ionization in Arrhenius theory shows the presence of hydrogen ions, which, since the hydrogen atom only has one electron, the hydrogen ion is simply a proton. But it turns out that this chemical entity does not exist very long in water. We will start by addressing the final point first, and that is the presence of hydrogen ions in water, or the lack thereof. It turns out when that acid releases its hydrogen ion, or when the acid ionizes, that hydrogen ion immediately bonds with a water molecule to form a hydronium ion, H3O1+. Even though the hydrogen ion does not exist in water, we will still, on paper, often refer to the hydronium ion as just a hydrogen ion for sake of simplicity. But what you should be familiar with is being able to move between talking about hydronium ions to hydrogen ions to protons because they are all the same chemical entity. We will see when we start to look at the stoichiometry of these reactions, it doesn't really matter whether we refer to it as a hydronium ion or a hydrogen ion. The stoichiometry will all work out the same. Rather than defining acids and bases as chemicals which produce specific chemicals, the Bronsted-Lowry theory of acids and bases define acids and bases in relation to each other in terms of which one donates and which one accepts a proton. In the Bronsted-Lowry theory, an acid is defined as a chemical that is a proton donor. A base is a proton acceptor. What's important in this theory is that you cannot have one of these without the other. If a substance is donating a proton, there must be another substance which is accepting the proton. So acids and bases always come in pairs. Let's look at an acid-base reaction and see how we identify the Bronsted-Lowry acid-base pairs. The way we're going to look at that is thinking about who donates the proton and which chemical entity accepts the proton. We will look at this reaction initially moving from left to right. So we have ammonia and phosphoric acid. The way I will track the movement of a proton or a hydrogen ion is to look at what happens to each of the chemical entities as we go from the left side to the right side. We see that the nitrogen compound, ammonia on the left-hand side, as we move from left to right, has gained a hydrogen, NH3 to NH4 1+. So it has accepted a hydrogen. Where did that hydrogen come from? Well, we can see that phosphoric acid has lost one of its hydrogens as it went from phosphoric acid to the dihydrogen phosphate ion. Phosphoric acid is acting as a proton donor, and ammonia is acting as the proton acceptor, the base. As you can see in this reaction, I have an equilibrium arrow, and which indicates that we have a reversible reaction here. And in fact, we are going to be looking at many acid-base reactions which are reversible. In the reverse reaction, the hydrogen is just going to move the opposite way. So if I'm looking at this reaction from right to left, the ammonium ion is donating the hydrogen, so it is acting as an acid, and the dihydrogen phosphate ion is acting as the base. It is accepting the proton. In order to distinguish between which acid and base we are talking about, the convention is that the chemicals on the left-hand side are just referred to the acids and bases, and the chemicals on the right-hand side are referred to as the conjugates. So NH4 plus is the conjugate of NH3. They are an acid-base conjugate pair. H3PO4 and H2PO4 1- are another acid-base conjugate pair. In the previous question, we looked at substances on the left-hand side which were obviously acids and bases. Here we have two substances which neither of them have the hydroxide ion present, and we both think of both of these as acidic substances. We have the hydrogen sulfite ion and phosphoric acid once again. If we look at what happens to each of those chemical entities going from left to right, we see that once again, the phosphoric acid molecule donates its hydrogen to the hydrogen sulfite. So the phosphoric acid is our Bronsted-Lowry acid, the proton donor. The hydrogen sulfite ion, being a proton acceptor, is the base. On the right-hand side, if we look at the reverse reaction, we see that the sulfurous acid, H2SO3, is acting as an acid. It is donating the hydrogen to the conjugate base, which is the H2PO4 1- ion. We will learn later on how we know when we have substances which could both act as acids, which way that hydrogen is going to go. But for right now, in identifying the pairs, we're just going to compare the chemicals on the left side to the right side and track the movement of the hydrogen ions or the protons. Our final concept for this lesson video is learning about the auto-ionization of water. Turns out that even in pure water, water is always splitting apart. It's not happening at a very high level, but some water molecules are ionizing, forming the hydrogen and hydroxide ions. This system in pure water is at equilibrium, where the reverse reaction's also happening, where the hydrogen ions and hydroxide ions are recombining to form the water molecule. If we have an equilibrium system, we can write an equilibrium law expression. Because the water on the left-hand side is a pure substance, the equilibrium law expression for this is just the product of the hydrogen and hydroxide ion concentrations. The equilibrium law constant in this case is given a special symbol called KW. the auto-ionization constant for water. At 25 degrees Celsius, that constant value is 1 times 10 to the negative 14. And recall that when we have a very, very small number like this, that means that the equilibrium lies very heavily to the left-hand side. Or in this case in particular, that number is telling us that most of the water is unionized and there's a very small concentrations of the hydrogen and hydroxide. Here's the KW expression once again with the specific numeric value substituted in for the KW. This equation is particularly useful because it will allow us to convert between hydrogen ion concentrations and hydroxide ion concentrations because that KW value on the left-hand side is always known. There is another useful equation that we can derive from the KW expression. If I take the negative log base 10 of both sides of the KW equation and apply the log product rule, we get an equation that looks like this. The right-hand side contains two values there that we often refer to as pH and pOH. If we take the value of negative log base 10 of 1 times 10 to the negative 14, we get the value 14. When you add the pH and pOH of a solution, they will always sum to be 14. This summarizes our introduction to Bronsted-Lowry acids and bases. The three things that we looked at specifically in this video were identifying Bronsted-Lowry acid-base conjugate pairs, introducing the KW expression, and two different versions of that KW expression, which will allow us to convert between talking about acids and talking about bases, talking about pH or pOH or hydrogen ion concentrations or hydroxide ion concentrations.